This book has many chapters with many topics, but once again, we're going to concentrate only on the homework assignments, but be sure to read all the material. The first concept is the relationship between the frequency of a signal that is retransmitted, the speed of light, and the wavelength lambda. The speed of light is because radio waves travel at the speed of light. Let's say we're trying to transmit a signal that is 55 kilohertz in frequency, and that we're going to transmit through space, so that speed of light is 3 times 10 to the 8th meters per second. And what we need to find is the wavelength, or the length of one wave. The formula says that the wavelength lambda is equal to c divided by f. In this case, if we solve for lambda, we see that the wavelength is 5,455 meters. And why we need to know this is the antenna then for transmitting or receiving the signal is theoretically 5,455 meters long. This is a huge antenna. Let's say we're trying to send a signal through water, and in this case, the speed of light slows down. And so now we don't use c, but we use v. But this time then, the speed of light is zero point 0.5 times 3 times 10 to the 8th meters per second. So we modify our formula to say that lambda equals v over f. This time we're trying to transmit a signal that's 1 megahertz, and we're traveling now at a slower speed. So the formula becomes lambda is zero point 0.5 times 3 times 10 to the 8th meters per second divided by 1 times 10 to the 6 hertz. And then the solution is that we have a wavelength of 150 meters. And so we notice that the higher the frequency, then the shorter the wavelength. In practical communications, it is found that 1/4 lambda is good enough to send or receive a signal. So in this case, 1/4 lambda would be 37.5 meters. It's a shorter antenna, but still pretty good size antenna. How much signal in bits can be sent through a given channel of communication depends on Shannon's rule, which relates the capacity, and it depends on the strength of the signal, the strength of the noise, and the bandwidth. So P sub S is signal power, P sub N is noise power, and BW is bandwidth. Let's say that you have a signal power of 150 watts, and that the noise is 12 watts, and you have a bandwidth of 2 kilohertz. How much signal can we get through here in bits per second? The formula says that the capacity is equal to the bandwidth times the log of base 2 times 1 plus signal power divided by noise power. We plug in the numbers and we begin to simplify the formula. And then we get to the point where we have that the capacity is 2 kilohertz times log base 2 of 13.5. Now, dealing with base 2, it can be difficult, so there is a simplification. It says that the log base 2 of any number n is equal to the log of n divided by 0.301. Let's finish the simplification by taking the log of 13.5 dividing by 0.301 and multiply times 2 kilohertz, and we find that the capacity is 7,510 bits per second. What we can learn from this example is if we're going to improve the capacity of our channel, we need to increase the power, lower the noise, but more importantly, to increase the bandwidth. And this will give us more transmission of bits per second.